Hello and welcome to today's Wolfram Institute live stream. Today we have Kiran Shrestha, um, worked for Applied Materials for 24 years as a software engineer and then software tester, then algorithm developer. Kiran attended this summer's Wolfram Summer School, where I had the honor of mentoring him. Quite a pleasure. And today Kiran will be presenting his summer school project on continuous cellular automata, analyzing the effects of small perturbations on input conditions. Kiran, welcome. Thank you for coming on, and you can get started with your presentation.
Thank you. Thank you so much, Dugan, for the introduction, and thank you all for coming to attend my talk. I really appreciate it. I hope to, um, um, by presenting and sharing this with you, I hope to learn more about this subject myself as we go through it. Okay. So the title of my talk is Exploring Continuous Cellular Automata with respect to small perturbations. Um, so the main motivation for this project was that um, in the book by Christian Beck, the book titled Spatio-Temporal Chaos and Vacuum Fluctuations of Quantized Fields, this reference number 5 here. It has some predictions of some fundamental physics parameters based on what are called chaotic strings. And in this reference 3 by Carl Detman, an article called Stable Synchronized States of Coupled Chebyshev Maps. In it, the author analyzes the chaotic string theory, and he raises a couple of questions. And when I read Stephen Wolfram's book, A New Kind of Science, I realized that Stephen's book, NKS book, has some explanation which might throw some light on to Carl Detman's questions about chaotic string theory. So when I joined the summer school this year, I talked to Stephen, and he suggested to me to explore these continuous cellular automata. Chaotic strings are a special type of continuous cellular automata. So Stephen suggested to me to explore these continuous cellular automata with respect to small perturbations, which might help to address the concerns and the questions that Carl Detman raised regarding Christian Beck's chaotic string theory. So that's the motivation for my project. So we investigate different neighborhood sizes and activation functions for these continuous cellular automata. Continuous cellular automata are basically normal cellular automata, except that the value on each cell is a continuous real parameter instead of binary. So that's the only difference. And Stephen also mentioned to me that since neural networks also involve continuous real numbers, connections with neural networks also. We study these continuous cellular automata by investigating different neighborhood sizes and activation functions and see how small perturbations affect their evolution. And we classify the resulting automata according to their complexity. We'll see some pictures below. And we investigate intrinsic randomness generation and sensitivity to initial conditions. Stephen Wolfram's NKS book helped me to, it opened my eyes a lot regarding these fundamental issues of intrinsic randomness generation and sensitivity to initial conditions. So we'll investigate these 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 things in the case of various continuous cellular automata, and also in the special cases of these chaotic strings. Um, so we hope to build a computational tool to study the foundation of chaotic string theory and clarify some of those fundamental questions using Wolfram Mathematica. Okay, so so we cover these. Um, So overview, in section one, we study various types of effect of small perturbations. We'll see some graphics there. And in section two, we study, we explore intrinsic randomness generation and sensitivity to initial conditions on some continuous cellular automata. And in section three, we specialize to the chaotic strings, which are a special type of continuous cellular automata. Um, so, um, okay, there you go. In this section, um, we use this following algorithm, which I named algorithm one, to do the simulation. Corresponding to each cell, we take the average of all the cells in its neighborhood and apply the activation function to the average. And then we subtract the average of the neighboring cells from the value of each cell and take the absolute value. And this is simply to help filter out some stripe patterns which are not central to the main pattern. And the initial value is 1 minus delta, where delta is a small variable perturbation within this range, 0 to 100th. And we vary the value of delta and see what happens. And it turns out we have three categories of results. The first category is one where it's stable with respect to small perturbations. And the second is sensitive with respect to small perturbations. And the other is sensitive only at some particular threshold values. So I found those three categories. And here's the main code. If we need to, we can dig into this section, but we'll minimize it for now. And this is the manipulate function. Um, um, so let's see. Yeah, I defined the activation function here in a general way. So there are some parameters which, when varied, helps to give these different activation functions. And this is the cellular automaton plot. And these are the parameters involved here, this and this. This I put it just to make, yeah.
Um, can we go over the definition of what this cellular automata model is set up to be? That is, I don't know. We can review for the audience the pages in NKS that talk
Oh,
about this.
oh yeah,
Okay.
we can do that. Yeah, we can do that. That's a good idea. Yeah,
I
let's.
can share a screen or send you a
Yeah,
link.
I can do it here also.
Okay.
So we can go to the reference here, Stephen's book. Here's the online version. Actually, let me see. Oh, okay. Can you see the screen?
Hmm.
Okay.
Yeah, I think it's on page
So
156.
156. Okay. Systems based on numbers, I think. Um, this one, it's 155. Yeah.
Oh, okay.
156. Okay. Yeah, this is a very nice illustration of how a continuous cellular automaton works. So in this example, there are zeros here in the first row, except this single cell, which has one. Um, and then when we apply the, let's see, a continuous cellular automaton in which each cell can have any level of gray between 0 and 1. The rule shown here takes the new gray level of each cell to be the average of its own gray level and those of its immediate neighbors. So for example, 0, 1, 0, the average is 0.333, one third. And so these three um, uh, uh, let's see, 0, 0, 1, 1 divided by 3 is one third. 0, 1, 0, this is 1. Oh, that's good. Yeah. And the average is one third, and so on. And the rest are 0, 0, 0, 0, 0, 0, and so on. And that's the algorithm we iterate throughout.
And then
So,
here again, it's like this one here is adding up these three values and taking the average. Uh, and so it's still a neighborhood of three from
yeah,
one row to the next. And then, um, yeah, exactly. Okay.
yeah, um, yeah,
And
yeah,
then so
that's
in,
great.
in this model,
And
like the value here is being distributed evenly as it goes down, and I think that the sum of each row turns out to be one. So this one value is being redistributed throughout all these rows in a diffusion model
mhm,
that just kind of diffuses. And so this sort of simple initial an initial first case of the continuous cellular automata. What makes it
mhm,
continuous is not the fact that the boxes here are still discrete, um, and so it's not having a continuous domain of
mhm,
ranges there. It's still a discrete grid, but
yeah,
the values in each of these discrete cells is allowed to be a continuous number.
exactly.
And then
Yeah.
and
And
then
in our case,
mhm.
yeah, yeah, go ahead.
And then you can go on to the next page.
Oh, okay. Yeah, so I just wanted to mention in our case, instead of taking simply the average, so in this case, it's the uh, the x y equal to x identity function. In the general case, we apply some activation function to the average. So okay.
Oh, what? I'm sorry. Can you go on to the next page there? Because that shows the a
Oh,
different
oh, oh,
activation.
oh, oh, yeah, 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 yeah. Oh, yeah, that's true. Yeah, 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 yeah. It is here already. Yeah, yeah. This is a nice example. Yeah.
Mhm.
Well, instead of the uh, the identity function as here, which is simply translates to input equal to output. Here we have this fractional part of 3/2 times the input, and this is the result of the applying this
Right.
rule.
So again here, just for the sake of clarity, so here the function is take three values, add
Mhm,
them up, and then uh, take the mean and put that
mhm,
mean into this function, this activation function here. So there's a sort of discontinuity and a resampling. Um,
mhm,
so it mixes up the values. So when you plug one third into this value, it hits
mhm.
zero point 0.5,
Yeah.
something like that. And
Mhm,
yeah, exactly. And so um, that activation function changes the dynamics of the values in this thing, in the
mhm,
cellular automaton, and you
mhm,
get a much very rich pattern. Um,
mhm.
and in a lot of cases, you get patterns that you don't really see in the
Yeah.
standard discretized
Yeah,
cellular automata model.
yeah, yeah. So, which is very impressive. And on the next page, let's see, we have another example. Um, well, uh, detailed explanation. And then, yeah, in this page, there are more examples. And we see these stripe patterns as part of the, um, following the rules. So earlier when I mentioned these are the stripe patterns I was referring to. And when we apply the second step of the algorithm that I showed earlier, that helps to avoid these stripe patterns and focus on the main central pattern here.
Right, right. Yeah. So the stripe pattern happens when the activation function has a non-trivial
Yeah.
bias to it.
Yeah,
Um,
and in this Stevens book, he used only one side of the. When we subtract off, it's subtracted off only on one side. But Dugan and I, when we worked on this, we decided to subtract the average of both sides of the cell. So that's the only small difference. But qualitatively, the results are similar. So this central example in Stevens' book, he shows this removal of these stripe patterns.
right. So the horizontal stripes are usually
Mhm.
uniform
Yeah.
in value to the left and to the right of the central figure. So
Hmm.
if at every as a post process to the image, you take the difference of two neighboring pixels.
Hmm.
If they're on the same stripe, then the
Hmm.
difference will be zero. If
Yeah.
if they're on the part of the stripe that isn't changing, so you can get rid of the stripe pattern and just look at the difference.
Yeah.
And yeah, as you said, uh, Steven, in this example, he just says, okay, well, what is the difference between one pixel and the pixel immediately to the right of it?
Hmm.
Um, and we adapt to a different model that's symmetric. Says, okay,
Hmm. Hmm.
so how much does one pixel differ from the neighborhood of to the left and to the right?
Right.
And so we have the activation function and then that sort of difference of filtering, and
Yeah.
that's the continuous cellular automata that we are looking at in the project.
Yeah. 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 Thank you, Dugan, for helping to clarify this. Yeah. This is very important to clarify. Okay. So let's see. So we can move on, right, Dugan?
Mm-hmm.
Okay. Um, so yeah, in this manipulate function, we have this radius of the neighborhood 1, 2, or 3. Um,
I really like that.
uh,
There's a lot going on even in that one. So we have like a polynomial, a cubic polynomial activation function,
mhm.
um, and what's interesting here is sort of I don't know if you could like expand that. Oh,
um, let's see. Okay. Expand which one? So, oh, this
the
one?
plot.
This one? Oh, you
Make
mean
the
this one?
plot bigger.
Oh, sorry. Okay. Yeah. Okay.
Hmm. Um, okay, so it's like there are pockets of reducibility in this, um, where the vertical stripes are, and then they're sort of like dendrites that are
Yeah.
coming out. Um,
Yeah.
it looks like you have a. Can you scroll down a little bit, actually?
Mhm. Uh, this one? This one was for radius equal to 1. That's
I see.
more. Uh, there you go.
Oh, okay.
Uh, yeah.
There it is. Yeah.
Mhm.
Yeah, I really like these bands that kind of come in.
Mhm. Mhm. Mhm.
All right.
Yeah.
And so that manipulate is like you can change the parameters of that activation function.
Mhm. Mhm. Right. So, yeah, yeah, these are the different parameters. Yeah, and this is the delta. Um, if I change this slightly, it'll take a few seconds. And there you go.
Mm.
So, yeah, that's the idea. So we can experiment with this.
Right, right. Um,
Yeah.
and
So,
it's very sensitive to the parameters of the activation function also.
mhm. Yeah, yeah, like, mm, see, yeah, it's suddenly a very different pattern.
Hmm.
Yeah, yeah, it's interesting. And so once we find a certain interesting pattern, um, uh, we can record that by copying these parameters here. And then, so that's what I did. So this is a sample code for the specific cases. So this is one example, I mean, kind of frozen example. Um, so this is the dynamic interface here, and we can save some interesting patterns. Like here, results stable. For example, in this category of stable results stable with respect to small perturbations. So, so if I use R equal to 1, A equal to R, A, B, C, D, K, P, delta, N, these are the values here. So this, um, let's see, this is a bitmap. So I can go to the other Mathematica notebook to expand this if we want. It's, let's see.
So
Um,
R is the radius of the cellular automata model, and then
the
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 ABC is
neighborhood.
the
Yeah,
neighborhood.
the
Yeah.
neighborhood. Yeah, yeah. So let's see. In this file, we have, um, let's see, experiment results table, class one. Yeah. Oh, um, oh, here also I put the bitmaps.
Mhm.
Okay, in some of the other results, uh, there are the actual output files. But anyway, here this is an instance where um, um, even if we change the value of delta, this pattern does not change. So this is under that stable category. And even under that stable category, there are different classes. Class one, meaning after this step, it's just empty, I mean, zero. That's the Wolfram classification. So class one. Um, so after this, it's just uniform pattern after a certain stage. So this is under class one. And class two, it's repetitive. That's the definition of class two. So after, in this case, when you use these parameters, it repeats after soon after the start. So this is
So the
class,
the class
yeah.
one, it's a finite lifetime, which is itself not trivial to achieve. Um,
Oh yeah, yeah, yeah. In one of the tech conference talks, one of my friends talked about this um, their project where this having a finite lifetime was the main goal of searching through the computational universe of these certain types of cellular automata.
Hmm.
So yeah, um, actually, it was the goal was to have as large a lifetime as possible, but not infinite, finite, but as large as possible. Yeah. So anyway, this is an interesting case example of that. I mean, finite lifetime. Okay. So this is class two. This is class three. Um, Rather random looking, somewhat similar to Rule 30, but it's symmetric by its definition. It's symmetric, um,
Hmm.
but there's a lot of random looking patterns here.
Yeah, a lot of
Uh,
triangles as well.
yeah, a lot of triangles. And class four, this has some uniform regions as well as some um, random looking patterns. And yeah, there are some, various structures. So I put it in class four category.
It's
But in
interesting
all
because
four, hmm?
it's like it's doing some like wild stuff at the beginning, and then it takes
Mhm.
time before the simple, uh, repetitive structures start to come into it.
Yeah, 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 yeah. Yeah, it's really interesting. Mm, yeah. So what was I going to say here? Um, okay, uh, I'll go back if I remember. I was going to say something about this, but anyway. And another category is results sensitive with respect to small perturbations. Uh, uh, oh, I think all I wanted to emphasize was the fact that for all these four cases that we just saw, uh, even when we change the value of delta, it does not change. The pattern remains the same. And the other parameters remaining the same, with just the delta varying. These are stable. That's why these are under this category, stable with respect to small perturbations. And the small perturbations are within this range, as I mentioned, um, 0 to 100 in steps of this much. So, okay, so that's stable category. Um, and the other one is sensitive category, sensitive with respect to small perturbations. Um, there were no class one uh, cases. In class two, uh, this is one example. So this is a bitmap. So when we change the delta value, this pattern changes a lot. Um, so this is a repetitive pattern, so I put it in class 2 category. And similarly, class 3. This also pattern changes when we change the delta value. And by the way, these are the activation functions on the left here, the corresponding activation functions. And this is different from this one, for example. And class 4 again, this is in when we change the delta value, it changes, but this is in the class 4 category.
Hmm.
And the third category is uh, sensitive only at particular threshold values of the perturbation. So I put two typical cases for each case, subcases for each case. For example, again, there's none for class one. And starting with class two, if we have, for example, delta equal to 0.00132, we have this pattern. But if we change slightly, 0.00133, only the change in the last decimal place here, then it dies out pretty quickly. It's zero
Yeah, let me
down here.
no. I'm also sharing screen, um,
Mhm.
trying this out. So let's look at some of these. I have my own notebook where I'm recreating these values, and
Um, mm,
well, if you go to
where's
there's
yours?
a tab at the top for
Huh?
sharing. Um,
My Dugan screen. Okay.
yeah,
Mhm.
yeah. Okay. So so here's the one with the finite lifetime, and then
Mhm.
the so I have the activation function here set up,
Mhm.
and
Mhm.
so it's starting with a single value of 1 at the beginning, and then going from there. And
Mhm.
this delta is changing the value that is at the initial condition in the center, top center cell.
Mhm.
So if I change that, let's see what happens. So it's pretty robust up near 1. There's a certain value around zero point 0.9 where uh, the actual lifetime gets longer, and
Mhm.
then kind of coasting through. At some point, there's a very discrete phase change where it just does this. Um, Pretty simple behavior still. I guess that's class 1, right? Simple
Mhm.
behavior.
Mhm.
But it's no longer finite. It goes infinite and then back to finite lifetime. Still the same
Uh,
shape, effectively.
or Dugan, I'm just thinking maybe if we go further down, it might be a large diamond shape.
Um,
Like
yeah.
like see
So
here.
yeah,
Yeah.
there doesn't seem to be that's a very interesting threshold that it doesn't grow
Mhm.
anywhere. Um,
Mhm.
and that might be something to look at
Mhm.
for that case.
Mhm.
Um, let's see some other ones where like this is
Mhm.
a kind of a chaotic one, and
Mhm.
if I change the value of the initial condition, um,
Mhm.
it changes quite a bit, but sort of only in the center. Like there's a lot of stuff that was just unperturbed along the sides, um, which is
Mhm.
itself very interesting. Uh,
Yeah.
and sometimes there was a change in there that didn't happen until very late in the evolution. Um,
Mhm.
yeah, very cool stuff.
So it's interesting that it's not I don't know if you can see my mouse. Can you see my mouse moving?
Um, I unfortunately can't.
No.
Um,
Oh, okay.
I can see your
Um,
on your screen when I look at your screen. I can see your mouse there, but
oh, okay.
there should be a way for you to draw on Zoom something. Do you have?
Oh, there's this drag to move. Let's see. Um, let's see. Oh, yeah. Can you see now? Can you see the circle?
Oh yeah, yeah, yeah. I can.
Oh, okay, okay. So beyond this point, it's interesting that it doesn't expand, right? It just is that it, Dugan?
Mm-hmm.
So
So this is
it,
a periodic
uh-huh.
boundary condition. So along
Oh,
it wraps around on the sides. Um,
okay. Is it because of the wrapping then this slope ends here?
right, that's going off the boundary of the plot
Oh, okay, 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 okay.
of the pixel grid, which is sort of not shown but implied.
Mhm.
Yeah, exactly. Um,
Okay.
But yeah, so there were some other interesting examples. For instance, let's look at this one. So this is a zero point 0.6 slope and a 0.785583. I'm gonna forget that, but the slope is 0.6. No, that wasn't it.
Wow.
0.78. I'll just write that down.
Mm.
Oh, I see. There we go. Okay. So this does a couple. It does a little bit of stuff in the center,
Mm.
and then goes to repetitive phase. But the two
Mm.
like little repeaters keep like encroaching in, then they
Mm.
collide, and then they split apart, and then these two little nubs at the end just sort of like stop doing stuff at that point
Oh.
forever. So it's
Oh.
another finite lifetime,
Yeah, yeah, yeah.
and but maybe like a class 2 or 3 finite lifetime. Like it's a little bit chaotic. Um,
Mm.
but again, we see some similar behavior if we change the delta, the value of the initial center pixel.
Mm.
Um, Here it splits off. We saw that phenomenon before with that other finite lifetime one. Um,
Mm.
and then let's
Mm.
see if it, and then it's very stable in this region for these values. So it's like it was sensitive, and then there's a phase change, and it was like
Yeah,
discrete
yeah.
values, and then another discrete change, and then back to something which is a finite lifetime.
Mhm.
So yeah, very interesting,
Mhm.
very interesting.
Yeah.
Did you think of doing some kind of like effective cellular automaton, like for instance, restricting to some strip in the middle and trying to somehow prescribe some boundary conditions and study if maybe you prescribe somehow easily some boundary conditions and it would in the strip in the middle would recover actually some, because it's always about you are always when you look at it you are always seeing what's happening in the center, what's happening on the side.
Mm-hmm.
So maybe someone could come out somehow average out the behavior on the side and somehow study what would happen to the cellular automaton with the boundary condition. Maybe it would kind of, yeah.
So what do you mean by boundary condition? Like have like um, structures on the left and to the right of
Yeah,
prescribed values, and then
you just take like 10 fields in the middle and
mhm.
prescribe, take like sinus or cosinus, let's say on the side and or take constant minus 0.3 or something like this on one side, constant plus 0.3 on the other side, and study what's gonna happen.
You mean apply different functions at the boundaries?
Yeah, I mean, you would have like two boundaries. You would have like a
Uh-huh.
cube, right? You would say what are all the values outside. You would prescribe them using some kind of some effective some function, right? That you would kind of not be interested in what the cellular automaton is doing out of the strip. You would kind of just let it evolve in the middle of the strip, and outside you would kind of describe it by some potential or something like this.
Hmm.
Just some
Oh,
kind of
different types of boundary condition, huh?
Yeah, that'd be interesting.
and
Yeah, there's a lot of
also.
unexplored territory with this topic.
Uh-huh.
On these cellular automatons, you may have some operations, right? You can add these two together, right? You have some sum of such cellular automatons, right? You can multiply them with constant, because kind of they have like continuous values somehow.
Mm-hmm. Yes, exactly. Um,
Yeah, yeah, that reminds me, there was one paper where um, some where different types of boundary conditions were used on chaotic strings. Yeah, yeah, that's very interesting. Then, yeah, there's a lot to explore here. Yeah.
okay, so that's a flavor of the perturbative effects that we're looking at. So I'll go back to Ellen. Did you have a question?
Yeah, I wanted to, was Powell saying that it might be interesting to sort of set some boundary conditions sort of a priori and then figure out what are the parameters that might exceed those boundary conditions? So is it sort of trying to understand the underlying condition, the system that sort of makes the image go wider or stay within the some constraints.
I think he was saying, implying that it would be interesting to fix the width of the strip and then calculate that, and then along the boundaries of that strip, prescribe different values for those pixels and see what the effects of that constraint
Okay.
are. Yeah,
I see. Yeah.
which
I have to admit, I have trouble kind of motivating conceptually the continuous cellular automata. I mean, I understand, and they're very beautiful, and I can see that it's like a fascinating sort of rabbit hole to go down. But I wonder, are these kind of just tricks for equivalencing in some sense, potentially discrete cellular automata, discrete rule systems that are kind of beyond our potential ability to perceive at the discrete level. So we're using these continuous cellular automata to sort of and to equivalence what it might be like to have discrete rules playing out at much lower levels that we can't even model. So we're is that why is that the role of continuous cellular automata?
I think it's just to open up the computational space for them, and a good motivation for it in my mind is um, I'll I'll share screen again, um, but the mollusk shells. If you see my screen here.
Not yet, not yet.
Oh,
Oh, there you go.
uh-huh. So here there's like a biological motivation that these shells are adding row by row when they grow the shell new cells, and those cells are discrete, but the amount of pigment in each cell is sort of a continuous concentration between 0 and
Is
maximum.
Is it though? Do you think?
Well, technically, it's like you have this cell, this region of the um, a cell on the shell, um, and it has a particular amount of pigmentation inside of it. But that pigmentation is given by certain proteins or chemicals or whatever it is, and the number of chemicals in that like little cell is some number, but probably in the thousands or millions or something like that. So there's a high dynamic range of different amounts of pigmentation that can be exhibited in each cell. Um, but it's again like it's not really discretized to like just three values of pigmentation. This is um, whatever it is. I'm not sure, but it's probably best modeled on a continuous cellular automata schema.
And also in these natural continuous looking cellular automata, we know that everything is granular at the bottom. So maybe we can think of these as discrete cellular automata with lots and lots of states.
Mhm.
Yeah, so in that case, like these continuous ones are kind of, it's just a trick to to do some kind of equivalencing
But
on top
a
of
very
a
interesting question.
much more nested discrete system.
Yeah, that's a very interesting question, Ellie. Yeah, I think Stephen also talks about it in his NKS book. It's very amazing that we see discrete looking patterns in continuous cellular automata results. Uh, so I don't know. It may have some fundamental connection. I mean, fundamental connection or relation between discrete and continuous cases.
Right.
This would kind of also correspond to kind of what you said. This interpretation is some kind of average of some smaller microstate. Like this is describing some macroscopic behavior, and each element of the macroscopic behavior can view as a box where there is like other cellular automaton, smaller discrete one working. This would also kind of correspond to my point of view on that, I think.
Yeah.
With the boundary conditions. Yeah, I mean here
No,
like
no,
for the
so no, like I meant the macroscopic, microscopic thing. What, yeah.
it's
Yeah,
interesting to
the
think
more I
about
think
also.
about these systems, yeah, the more I think it's really discrete all the way down. And so anything continuous is really just a trick for observers like us in our universe that we have, harnessed this cool tool to be able to describe systems that are way too detailed for us to model effectively at the discrete level.
Mhm. Mhm.
Can't you try, Dugan, this may be even something that you could live code. Can't you try going from continuously down to discrete? Run basically the same transfer functions where the values are integers up to about 1 million,
Sure.
right?
Mm.
And then see if you get the same macro behavior. And if you do,
Oh.
crank that 1 million down to 1,000 and see what you get. Okay, because I'm wondering if the macro behavior is, well, we're saying it's continuous. It's not continuous, right? Nothing's really continuous if you're running it on a computer. There's it being continuous means that you've got a ton of states.
Mhm.
And if you had a ton of discrete states, would you get similar looking behavior?
Yeah, that's a good question. Yeah,
Yeah.
yeah.
I can almost imagine a metric of some sort that sort of tells you how many states you need to have in order to kind of replicate a certain type of continuous of phenomena.
Mhm.
Not sure which. I like this idea of a threshold.
I mean,
Yeah. So here I'll
continuity.
experiment with the threshold of rounding everything to the millionth
Exactly. I
and
think
then
that's the
um, seeing what happens. So it looks right.
Dugan, can
Mhm,
you go up a little bit on your screen?
mhm.
Okay, there. Um, let's see. Your round 10 decimal. Are you using, I'm wondering, are you using floating points or?
Yeah. Yeah. So
Um, uh, when I did with machine um, precision, Remember, Dugan, you pointed out, for which I'm very thankful. You pointed out the asymmetry in several of these cellular automata plots, which I did not notice before. You pointed out to me.
Mm-hmm.
And we realized that it's because of the asymmetry, which should not exist, which was very subtle to notice. And you noticed, and I really appreciate that because that slight asymmetry, which should not be there because of the rules, the symmetric rules, the asymmetry should not appear. And you noticed the asymmetry, and it turned out to be because we were using floating points up to that point.
Mm-hmm.
And I used the rational point, I mean, exact fractions, and then the asymmetry went away. So I'm
Right.
wondering, in your the one that you're showing just now, it seems to have some floating point. Would that cause any problem? Or is it not relevant part here? Let's see.
Right. So taking out the rounding,
Okay.
going back to the original. So
Mhm.
I noticed that for when the activation function has a slope, at least with these linear activation functions, when the slope is above a certain threshold. Okay, so these sort of Christmas trees are symmetric.
Yeah.
The rule for the it should be symmetric the way it's set up, because each you're taking a neighborhood and taking the total of it and then outputting a value. So however
Mm.
those the values in that neighborhood are arranged, it won't matter. So uh, basically these are symmetric and they should be, but when the so the symmetry sort of dies off right around here at this at this level, and
Mm.
um, and here again it's symmetric up until around here,
Mm.
and the and that has to do with the numerical precision at play with
Yeah,
floating
yeah,
point arithmetic.
yeah. Mhm.
Um, and so what I'm doing is sort of if you take this n and
Mhm.
add precision to it. So let's say
Yeah.
like floating point is up to 16 decimal places.
Yeah, something like that.
Okay, we'll try 32 and see if this helps. Uh, okay, well we have to go back to that. Okay, this will be a good place to start. So I'll bake that in 1.09.
Maybe in the meanwhile, another idea. Did you try to use geometric mean instead of the arithmetic mean?
Mm.
No, I haven't. So when you take like the in the function, yeah, no, I didn't. So okay, let me reduce the numerical precision, and then we'll see how far down
Mm.
seem to start. Doesn't seem to have any effect. or at least the way I have it coded. I'm not sure if it's
Hmm. Yeah, for efficiency, we do need to use the a high enough numerical precision. Uh, Ideally, we might use infinite precision, but it takes a long time in some of these cases. So I ended up using 10 raised to the power 4, 10,000 accuracy for all of these.
Oh wow.
Yeah.
Somewhere losing precision. I don't know where to maintain it, but or introduce synthetic non-floating point numerical, so software induced numerical precision. You're right, but okay.
But even if it's not fully precise, what breaks the symmetry?
Um,
You know, shouldn't the imprecision hit both sides the same way?
Uh,
yeah, I'm not sure
uh,
why it even then it's non-symmetric.
I think after the precision, the set precision is exceeded. I mean, the details involved are beyond the what is covered by the set precision or accuracy. Uh, I think there are some random effects that take over that cause this asymmetry.
Yeah, at first I thought I kind of had an intuition for why it would break the symmetry because there was I had this idea that there was kind of a progressive correction or not a progressive correction, but the correction would happen when this limit was exceeded, and then you would kind of reset progressively to be back within the bounds, the computational bounds that you're working within. But the more that I think about that, I'm not sure that that was the right intuition that I had when I was first, when you first mentioned that it breaks the symmetry because of the um, um, this level, these computational limits. But there might be something like that, that the way that the correction is it, how do computational limits get reset within a system? I don't know. Brian, I assume you know a lot more about how
No, it's again,
processes.
I'm not, because the thing is it's rotate left, rotate right, and the thing, you sum them together, right?
Mm-hmm.
You should get the same answer to the left and to the right, shouldn't you? And the sums should be symmetrical, and then applying the activation function shouldn't really have a way of breaking the symmetry.
But does that all computationally play out in a sense, like in in the same way that we see the plot results?
At some level, it should. That even if it's imprecise, it should be symmetrically imprecise, right?
Yeah, yeah, I think I agree with you. It should be, but then I thought, well, maybe there
Right.
is something about,
The fact that there's an asymmetry there it's a pretty good mystery.
yeah. I mean, one thing we could start to do is to round, yeah, do this rounding and to see if, as we increase the limits for rounding, at what point does that
Yeah, but Dugan, since how quick do you think you could quickly put a symmetry test into it? Take the thing as
actually,
as a big list of numbers, and rather than
yeah,
looking for
yeah.
broken,
Actually, in my sorry,
I
Brian.
was going to say, rather than visually looking at it, can't we just numerically look at it?
Yeah.
There's going to be a first line that's not symmetric, and we could just stare at those numbers and see what's going on.
Yeah, actually, in my earlier version of my computational essay, I did, well, in a way it was visual, in a way it was not exactly visual. I carefully, you know, folded, sort of, figuratively speaking, folded the cellular automaton evolution plot in the middle, folded like this, and then found the differences, corresponding differences, right and left, and then took the average value and plotted that and so on. So when we used machine precision, the asymmetry was very clear. But once we used the higher precision, it went away. So I'm thinking the rounding. Uh, so Brian, as you said, rotate right, rotate left should give the same result. Um, but maybe rounding in some, for example, uh, point 0 point. Um,
Oh, you know what it could be
uh-huh.
is rotate left. It's going to do some round. It's going to do two separate pluses.
Excuse me.
The um the addition needs to be done in an infinite precision way. The asymmetry could be broken by the fact that there's two plus operations.
Two plus operations meaning?
You're adding the list to the left rotated version to the right rotated version, right? And it's quite possible that after the first, it's almost like if you did an infinite precision plus twice and then rounded after doing the two additions, it would probably remain symmetric.
Mhm.
Okay, so here's the
Yeah, yeah,
the
that
symmetric
could.
difference of the
Mhm.
thing um,
Oh,
reversed on itself. So here, this is all symmetric, and then you can
But
start
that's
seeing,
really pretty.
yeah, that's fun. And so here you can see the deviation starting to creep up towards the top.
But isn't it showing a deviation even at the very top?
Um,
uh,
this is probably showing very small numeric deviation. Like, oh, on this side it's like 0.01, and this side it's 0.0, but up
Right,
to
I did,
a foot.
but that's kind of microscopically the same thing. They should be exactly the same. The fact that they're not exactly the same is confusing. Could you actually just focus in on one line? You know,
Hmm.
this is actually um why isn't even the very first line showing a deviation?
Yeah, it is.
So why is that?
Um, I don't know. I mean,
Can we look at the numbers? Maybe the way that you're doing the symmetry is, um, is the list an even width or an odd width? You know, because Dugan, in order for you to be checking for the symmetry, would have to be the width would have to be odd, so it doesn't,
Oh,
so the flip of it doesn't have that offset.
it's a center array, so it's like it's gonna be. Why is it even? It should be a certain
It should
number.
be odd.
Should be odd. So I started with a center array. Um, how do I change that? So the size is 500, or the size is whatever. Okay, so technically it should. Okay, so now it's an odd thing. I don't know. Okay, so I have this and the size is that. What does center array do? Let's look at that. I said like 1, 5. Okay, so it says like size 5, so it has 2 on the left, 2 on the right, and 1 in the middle. I'm controlling that.
And if you did center, can you just, so we're understanding this better, can you do that line again with 6 instead of 5?
Hmm. Oh, so yeah, this
Yeah, you got to give it an odd number or it's not going to be flippable.
right. Yeah, exactly. Okay, so that's why.
Oh,
But that doesn't explain the asymmetry. It just shows that the asymmetry detector was not doing the right thing.
so Dugan, earlier when you tested, it was oh, there you go. So now you're using the odd number.
Yes, yes. So
Oh, so that explains, right? Earlier, because you're using even number of cells, I think.
Yeah, and actually, 0 is gray.
I think so, right, Dugan? In this,
uh, okay. I don't know what I
there.
did to make it mad at me. Oh, that kernel crashed. Of course.
How do you make the kernel crash?
I mean, just it's with the front end, um, and I'm probably stressing it out a little bit because I'm having what do you call it? I'm sharing the
Oh yeah.
pixels from the window to zoom. Um,
There.
this is the symmetric difference.
Okay, can I take a shot in the dark?
Yeah.
Could you go back to the to the top of this, and instead of saying rotate left plus hash sign plus rotate right, change it to rotate left plus rotate right plus hash sign.
Like that.
Yeah, there's another instance of it about 4 lines further down.
Here, this one.
Yeah, why are there 2 instances of that?
Because here I'm doing a rounded version.
Okay. Okay, so does that change the symmetry story? No.
No.
Oh, actually, the fact that you changed it doesn't mean it's going to be changed inside of Mathematica.
Here. Okay, rounding it to discrete values does ensure that numerics don't get haywire. But I'm rounding it to the nearest tenth, so let's round it to something else. Okay, let me take out that. Let me go back to the unrounded, to the original. All right, so we're back to numerical precision falling out down the line. I'll close my other Mathematica windows I have open.
Are those Penrose tilings, Dugan?
Oh, did you see them?
Yeah.
Oh, I didn't know that it was sharing like that. Yeah, those were random pentagonal tilings.
Interesting.
Okay, so we're back to having this. And it's unsymmetric here. So like looking at so it's around here that starts getting unsymmetric. Look at the last line of the data. Yeah. A lot of numerical errors here and also there. So if I check the difference.
These are these the differences or the values of values themselves?
Um,
I
the
mean,
data
difference
and
between right and left, or
yeah, it's the cellular differences between neighborhoods.
the plot is for the differences,
Not the plot.
not the plot, right?
Hmm. Okay, here are the differences plotted for the symmetric difference.
Okay,
Mhm.
can you extract out the first line that is different? Or the last line that isn't different?
Oh, I see. Hold on. Okay, so it starts becoming different around here. 386.
Mhm. There you go. Mm,
And let me look at the previous line. So before it starts getting asymmetric, it starts having values that are boiling down to the numerical limit um, of floating point precision.
Right, but those really tiny values are at the edges and the asymmetry is near the center. So is
Yeah.
385 is th is 385 symmetric? Can't you do this by just subtracting it from its, yeah, that. So maybe could it be that the asymmetries are there much earlier, but they're just too small for us to be seeing them?
yeah, maybe we can try a few steps earlier.
Yeah, like look at like 10 rather than 3. Yeah, like look at it very early on.
Mhm.
You know, Instead of 380, try 10.
Mhm.
Try 2. Actually, try 1.
Ah,
1's good.
2's good. Was 10 good or no?
10 gave zeros, I think. There you go.
Yeah, 100.
Yeah, whenever.
I can tell. Dugan has clearly used Wolfram language a fair bit.
Yeah.
Oh, there we go. Can you put the number in them? Make the number more visible.
What number?
When does it, yeah, when does it start? Yeah, what's the index there?
I see.
Is it's there and it's just too small for me to see or something? Oh, yeah, it is there. It's just so
Yeah.
even very early. Yeah, yeah, no, it's just that the fact that you've got a much bigger screen than me makes me not able to see it.
Mm.
So if you go to the very, yeah, just like minus back to yeah, step through it.
Yeah, so even early on around oh, uh,
Around
12.
12.
Yeah.
Yeah, so what's happening between 11 and 12 is the question.
See. Let me just try writing this anonymous function. Okay, 11. SimDiff 0. SimDiff, we have this.
So that's interesting.
Yeah, that is interesting. And for some reason, it doesn't start perturbing the thing in any significant way until it's growing, and around what did we say, like 380?
386.
Uh huh. 385.
Could you see if you take 11 and add do the rotate left and the rotate right of it and divide by 3, is that still symmetric? Is it the addition that's breaking the symmetry or the activation function?
I think it has to do with the activation function.
But how does the activation function know to do something wrong?
Let's see. It's
It's a simple test.
378.
Can you
Hold on. interesting. Okay, so okay, here's the phase change at 379.
Mm.
And
There's a phase change there, but even way between 11 and 12, the crazy was starting.
yeah, so it have all this numerical stuff happening, very low broil. And the thing about the activation function is that, at some point you're doing this, you're doing this, you're doing this, and then you go.
Oh, and at some point it gets to, yeah. Okay, so, right. So it goes crazy when the error is crossing that divide.
Mm-hmm. Yeah.
Right. But it just means that the thing that we're trying to pin down just becomes more obvious at 378. Right.
Exactly.
Between 11, if we figure out what's happening between 11 and 12. So,
Okay.
the thing
Yeah.
that I was, if you take 11, you do date 11 plus rotate left date 11 plus rotate right date 11, see if that's symmetric.
Okay. Um, all right. So that's rotate left, rotate right, divide by 3.
Yeah.
And then we test this for metric
Yeah,
difference.
and test that. Yeah.
Okay. So taking the average of that works out.
Okay, but
And
that
then
means
then
the activation
yeah.
function. Yeah, the fact that if you run this through the activation function, it becomes asymmetric, then that's kind of weird. That it's kind of like pointing to some non-determinism of some strange kind in the activation function. Yeah, could you just go back to the way that we're testing it, run through the activation function and check the symmetric difference?
Okay, hold on. I have to get the values for that. So M is this, B is that. So it's MB 1.09, 3.329. And well, that's just oh, okay. So we have these values, and they seem to be, yeah,
These are symmetric, right?
Yeah.
And then you activation function it. Right, and the question is, does this remain symmetric?
It seems to remain symmetric.
Yeah.
Then is it the way that we're calling it in the manipulate different?
Isn't the
Hmm. Shouldn't this be doing the exact same thing as data 12?
That's what I was just about to check. Yeah, so it's like
You're running this just on your laptop, aren't you?
negative. I'm This is on my
Are you
desktop.
okay? Because one of the things that I remember hearing from Stephen is one of the reasons that LLMs aren't deterministic
Yeah,
is that
this is a good one. I love this
you
one.
yeah, it's running on a lot of different cores, and different cores will be implementing this exact stuff differently.
It was You would expect that addition is associative, but it's not true for floating point arithmetic.
Yeah. Right.
Is that
Or
what's hitting
even
us here?
what's that? It might
When
be,
I was
yeah, it
asking
might be the associativity, the
when I was
non-associativity.
asking when I was asking you to change the order of that, it was basically because wondering whether or not it's dealing, yeah, with arithmetic not being associative. Because you want to be doing these pluses in higher precision.
Yeah. So here I computed what should be the next, from 11 through this function. And if I subtract out what I get for data 12, wait a minute. What is this?
Are you doing this in the same
Oh, hold on.
precision as?
Wait a minute. Wait a minute. No, there's the difference. Okay, what are we doing? We're doing because this function All right. This is under the hood before the correction. You have the business with the stripes. So we're taking like neighborhood average, neighborhood differences, and doing that. So I think that's kind of what might be happening here. Doing abs differences. Whoops. Let's look at that. Okay, so it's going through the list. You want to take the difference between the center pixel and the pixels next to it on the left and right. And that might be where it's coming from. Okay. Right. So I'm guessing that, yeah. What was I just thinking? Oh, this. Not doing what it's supposed to. Oh, this is designed to work on like um, on a matrix, I guess. Really. doesn't look too bad. Small stuff on the side, but okay, so this should be computed values. And that, okay. Now it matches with that at 12.
Okay, and is the new one symmetric? If it matches with data 12, it can't be, right?
Yeah.
And it was symmetric before you ran it through that last step, the abs different list.
Mm-hmm. No.
So so abs differences list is breaking the symmetry.
This is breaking the symmetry. This here. So just taking the averages is breaking symmetry. Which is interesting. So hold on.
Right. No, so it's not the rotate left, rotate right, it's the averaging.
Rotate left, rotate right, plus itself introduces floating point errors for this. And these values are this size. So let me try taking app totals that. Should get the same answer, right? Yeah, basically. So what is it about um, okay, so 39. No, that's right, because it's like reversed. This one is here. That one is there. This one is here. Okay, so
This does look like it's going to turn out to be the arithmetic, the plus isn't associative. And I guess what you're trying to do is pin down the exact things that are being added that changing the order changes it.
okay. Yeah, yeah, it's not associative. Look at that.
What's the length of data 11 again? Is it odd or even?
Wait a minute, what happened? Oh, I see. No, the length should be odd.
Mhm.
It's odd. So here it is. So like Steven said, if I add the rotate right plus the original first, if I do right association to this, and then add the left rotated, then I get these values.
Mhm.
And if I add the rotated ones, if I left associate this triple, I get 0.
Wow.
And then from that point on, it's
From that point on, it grows.
mm-hmm.
So what does this mean in the big picture of what we're trying to do? You've got an unexpected source of noise that is growing.
Yeah, so let's see. Um, yep.
Hmm.
Now, how ubiquitous is that? I just took like random reals between 0 and 1.
Well, it's probably very ubiquitous, and it's probably rare that a 10 to the minus 16th difference is going to do things. It's just that, the fact that this is, that error is going to be amplified in each step.
Mm-hmm.
Do you remember the chapter in NCAS where Stephen was talking about like stretching and folding dough?
Yeah, sort of
You know, that,
making tasks
his point. Yeah, well, the point is if you're doing something that you're running something like a cellular automata, the errors amplify at the end of the day. You only are measuring the floating point behavior, not the thing in question.
Hmm.
But you could fix this by doing a sort.
And what is
Hmm.
the precision that we use above Dugan?
Would a sort do that?
If you took the three values and sorted it before and then applied plus to the sort, then it would always be it wouldn't the sort would kind of make it wouldn't care if it was associative because it would always be doing it in the same order. Right, you're adding three numbers together.
Uh-huh.
If you took it the simple example that you just did before of total one and total two, um, if rather what you'd need to do is make a list, but this would just dramatically slow it down. Make a list of the three numbers, sort the list, and then apply plus to it.
Mm-hmm.
The better answer, which may be looping back to what we were talking about a couple of hours ago, is just don't use floating point.
Hmm. So are we using floating points here, Dugan, or did you use higher precision?
Um,
This is floating point, looks like, right?
right, right. And so, um, right, this isn't introducing the error, it's up here. So, have those lists, I would have to map sort to.
Well, the thing that I was suggesting is instead of rotate left plus rotate right plus the thing, you make a list of those three things,
Mm-hmm.
then sort that list, and then apply plus to the sorted list.
Yeah, but these three things are themselves lists. So I would
Oh,
have
right,
to
right. You've got it. You have
have
to do to level down. Yeah.
transpose that and then map sort that, and then
But
total
the
that.
whole other approach is you can just avoid floating point and just do the whole thing with giant integers.
But you're right, did did solve the metric issue.
Well, so the question is, did that symmetric issue actually distort the results? You know, so if you go back and look at, we'll go back to the very beginning of the presentation and show the examples that you were showing. Um, was this just a fun diversion into analyzing how floating point works, or does this actually affect the core of what the session was about?
Yeah, so when Brian, when we did this, so we early on we found out the problem with this floating points. So at some point I tried um, exact the infinite precision thing, and the problem went away. But later on, for chaotic strings, especially for using the exact, rational numbers, the infinite precision um, was taking a very, very long time. So I used 1000, I think, at the beginning, 1000 accuracy, 1000 digit accuracy. And I used this symmetry testing, asymmetry testing function, and it went away. And later on, I was more conservative and used 10,000 accuracy. For all my results, and for up to I think 300 iterations. It looked pretty good. But after that, probably we may need to increase the precision. Most likely, much more beyond 300.
Well,
Um,
if you run a set of examples with 1,000 digit accuracy and then run it with 10,000 digit accuracy, can you see the difference?
up to 1000 digit accuracy, I use the function to confirm that the asymmetry did not exist.
Okay, okay, because the thing that I wonder is, and this was a comment I made like an hour ago, is at the end of the day, there was a comment made at some live stream before, is you've got to be a mathematician to think that there's a difference between 10 to the 240th and infinity.
Mhm.
Yeah.
Right. Right. So the question is, if you did all of the calculations with giant integers, would you actually see what you're looking for? Or would the fact that it was giant integers rather than continuous permute the thing that you're trying to examine?
Did you mean when you said giant integers, a ratio between giant integers?
Yeah,
Rational.
yeah, that,
Yeah,
rather than going between 0 and 1, you go
okay.
between
Yeah,
0 and 10 to the 50th.
yeah. So using giant integers in the case of chaotic strings, it was practical only up to 14 iterations or something like that. But using 1000 digit accuracy, I was able to go up to I think 200 iterations.
Right, but here's the thing: 1,000-digit accuracy and 1,000-digit integers should be the exact same thing, right? Because 1,000-digit accuracy and 1,000-digit integers gives you the exact same number of different possible states.
I think you're right. Yeah.
And having it be integers, you could be more comfortable that the math is well behaved.
Mhm.
Or at least you'd have a much clearer deterministic idea of what's happening.
Yeah.
Because the trouble that I had a friend of mine who was like an astrophysicist, and
Mhm.
he said you should just never use floating point because um, the thing is you always have floating point means you don't have to think hard about the numeric analysis
Mhm.
problems. And he just said using floating point doesn't solve them, it just hides them.
Right, right.
Oh, it seems
Yeah.
doing as you said, sorting those lists before adding them, takes away. It preserves the numeric. It preserves symmetry.
Hmm.
But this is a good cautionary tale, don't you think?
Yeah. Um, hmm. Now let's see if get a different picture. What's going on here? Using fractional values. Um,
Hmm.
so it's exact arithmetic. Oh, take away these. Oh, oops. Oh, it's taking too long to compute for the.
Hmm. Oh,
Yeah.
wow.
go to 200. Okay, so this is using just round to the 10th. Oh, huh.
So for delta using 20-digit precision?
Yeah, so as long as this, you start with that at the top, and then subsequent operations to that number carries with it every time that number is operated on it. It tries to maintain 15
Yeah.
decimal places of numerical precision.
Uh-huh.
And if I limit that, then it reaches that limit pretty quickly.
Mhm.
And then it goes to
Yeah.
black. But, for this, it seems like 20 is enough.
For how many iterations now? This is
500 iterations.
500 iterations. Okay, can you show the difference again? Difference plot?
Yeah, hold on.
So these are the differences?
Could you say, so you set a number up at a particular precision, and then all arithmetic maintains that precision?
That's the idea. That's how Steve described it to me at summer school.
Huh.
Does every row still add to 1?
That's a good question.
Because in some sense, I think is the spirit of this is sort of resource conservation.
No, because that was just the activation function. That was the identity.
So whatever it is that's propagating from 1 over time there's stuff that's feeding into it. Yeah, never mind.
Yeah, so that original activation function was preserving totality and just redistributing what was in the first
Right.
cell. But other activation functions will add material that's not there originally, sort of artificially.
Right.
Yeah, you have an offset, so to speak, and then there's the discontinuities involved.
Could you make activation functions that keep that?
I have to check.
Or at least that keep
Yeah.
track of what's been kind of put into the system so that, well, but I guess if you can always add something new to the system, that's not.
Yeah. So this B offset value for that the linear offset. So you have like the slope and then the offset. So whatever, if there's like if you're adding up three zeros and you have like a total of 0 and you plug that into the mx plus b formula, you'll have that offset will exhibit non-conservative quantity.
And the
So
slope also.
I'm not sure how to have activation functions which preserve what you're saying.
It's an interesting question, though, because
Mhm.
the idea of having continuous cellular automata that are really just sloshing things around, that could be really interesting.
Yeah, yeah. Um, where it's like it's trying to permute stuff and keep the total the same, and then you would want to look at like seeding that with a bunch of different positions of material.
Didn't we, in some conversation we had months ago, what was going on with swapping rather than weren't we dealing with cellular automatas that were doing swaps of various kinds? Yeah, vaguely remember that on like a triangular or hex grid.
Oh, maybe that's something that Ellie was doing,
Doesn't
or
sound
that was
familiar.
It may have been the person that was doing the triangular cellular automata.
Yeah, was that
yeah.
something with
There was something conserved with it, right?
Yeah, yeah, and it may not be the activation function as such. You'd need to like construct the thing differently to just think that at each step things are being moved from compartment to compartment. Though when we were talking about it the other time, what I'm sort of remembering is you had to do it in two phases, and it may be the case that you'd have to do it in two phases. That rather than, and this is something that came up a couple of times, is rather than actually having it be, you know, looking three cells to affect the center, instead look at it two cells at a time, do swaps between them, and then do the even partitions and the odd partitions.
Like, I think I remember what presentation that was. Um, Looking back.
It may not have been that one. Actually, Ellie, do you remember there was this question where we were talking about whether or not and it may in fact have been one that you did when it was talking about like the order of doing things that there were cells that each line was shifted relative to the one above it.
yeah, maybe. I mean, are you talking about chirality in a
I,
discrete?
I think all three of us are grasping and trying to remember what this resembles. Right. There was there was some stuff where stuff was conserved. And we're not remembering which talk it was where there was that conservative, there was stuff that was conserved.
I feel it's more likely Chase's talk than mine. Um, but
Yeah, maybe this looks this looks familiar.
This, with the hex grid.
Yeah, but I guess that doesn't look like the time we were talking about swapping.
Yeah, it was on the thumbnail for this, so I know it's in here somewhere, but
But actually, Dugan, didn't you like the fluid dynamics stuff had swapping in it, didn't it?
yeah, so that had collision rules for particles bouncing around.
Yeah, somehow this seems more fluid dynamics like. I mean, my takeaway from all of this, which is very interesting, is really just to think about how there's kind of ultimately any system faces computational constraints. And so, it's all about kind of equivalencing or dealing with those, all the implications of those constraints. This is freaking me out. It's really weird.
Sorry.
Thanks.
Can't seem to find it. But that thumbnail there, I don't know if you can see it. That's the something where something is conserved, or there's a little bit of computational reducibility going on. That might be what you're remembering.
Well, it's hard to remember exactly because one of the things is it at some very abstract level, whatever the rules are, the results all kind of feel about the same.
Mm-hmm.
Right, just the overall form of the kind of examples that we're seeing looked very similar to some of the other multi-state CAs that we looked at in the past. The idea of having these tendrils and, stuff looking like that they're moving around a little bit.
Yeah, and also the idea that, I mean, I find that mostly the simplest rules are symmetry preserving, or there's some way that even those that are not symmetry preserving can be applied so that symmetry is preserved. But it's interesting that when those constraints are, when the accuracy kind of is breached, that's where you get asymmetries. So I wonder if we could also think about asymmetry as a signal that a computation, like a limit, a computational accuracy limit has been met in a system. So even in systems where the rules are, like in theory, symmetry preserving, you can still have asymmetry.
Okay, so here we have total precision using fractions. So it's never going into any type of numerical world. I'll try to go to 300 and see. Oops. I'm gonna get some of this noise down here at least. How big are these numerators? Let's see.
I'm laughing.
What kind of 10 to the 1,000? Okay, my goodness. All right. How many universes is that? You know, 10 to the 80 is particles in the universe.
That's a question for Brian.
All right,
Well, how many universe depends on how big the universes are, doesn't it?
so
David Deutsch would claim that it all would fit in this one.
Dugan,
yeah,
um,
about 10
I'll
to
be
the
back in a few seconds.
Okay, okay.
Back in a few seconds.
Let me try for precision 20. Capture that. Interesting. Floating point. Okay, that's pretty drastic. Hmm.
I'm back.
All right. Well, that's been a journey
Yeah.
into numerics.
Uh-huh.
So if you'd like to continue your presentation or keep going through your what you found.
Yeah, this is a very important discussion here, which we have been going through, um, because because on it depends the validity of all that we've been doing. I mean, at least after a certain number of iterations, a finite accuracy or precision, um, always seems to have some limit beyond which the results may not be reliable, right? The results will be available, reliable up to a certain accuracy. Yeah, ideally, we could use infinite precision, but it's not always practical. Um, but it would be nice to have a good idea of, uh, you know, uh, what precision or what accuracy we need in order to base our results. I mean, to have reliable results uh, up to what number of iterations. I think it's important to know that. But as I said, for infinite precision, seems to be okay, um, but for finite precision or finite accuracy also, um, for a few hundred iterations, it seems to be good. But beyond that, we have to check. I mean, with more computing power and so on.
Mm-hmm.
So, yeah. But yeah, thank you. Yeah, for this very important discussion. Um, yeah. Let's see.
I'll go back to your screen, Kieran.
Okay. Okay. Yeah.
So we see a class
See.
2.
Can you see my screen?
Uh-huh.
Let's see, where's my screen here? But on my screen, I think, let's see. Oh, there you go. Yeah, we were here, right? Class 2, sensitive only at particular threshold
We
values.
can still only see
Oh no,
Dugan's.
Oh, sorry.
no. Ellie, if you change for you which screen you're looking at, because I'm still sharing. I'll stop sharing my screen.
Oh, right. Okay. Now I can see.
Yeah.
Oh, I understand. Okay.
So, Ellie, let's see. Can you see this subsection F?
Yeah, no, now I can see your screen. It's all good.
Okay. Okay, great. So, yeah. So this class 2, yeah, that's where we were. With this delta value of 0.00132, we have this pattern, and 0.00 for for delta value 0.00133, we have this. It immediately dies out after a few steps. So that was class 2. Class 3, again, delta value 0.00513, this pattern, and for delta value 0.00514, we suddenly have this pattern. So that was a sudden change.
Yeah, hold on. Let me capture that those values for
Yeah.
the one up top, because that is very interesting. And again, numeric. It might be numerics that is making that happen. So,
Mhm.
Yeah, that's a long distance to have like
to have nothing
this is
happening
yeah.
and then
Yeah,
something
yeah.
pops up.
Yeah, it is. quite surprising. Yeah.
But even though this may be on purpose rather than an artifact, doesn't that mean it's at the point where the activation function wraps?
Let's see. Activation function wraps.
Yeah,
This
there.
one,
Yeah.
0.7, right?
Yeah, because even though when we're chasing down that numeric artifact, the 378 or whatever it was looked like there was a big phase change, and that phase change happened, exactly when it wrapped from one node back over to zero.
Uh, um, Sorry, can you repeat that, Brian?
Oh, what I was it was um, not necessarily anything that was coherent. It's when we were trying to chase that thing down, we
Mhm.
found that there was a big phase change, and the big phase change happened because of the big jump in the activation function.
Trying to remember when that was. Okay,
Um,
but yeah, we can go back later. But um,
no, if you remember what it was, is when we were looking at it, the asymmetry started happening about 370 down. And the question is, why around then? And the answer seemed to be at that point, because it was at that point that the numeric values got to the point where just got a little bit bigger than one and then jumped back to zero, which which caused a phase shift in the overall behavior. So what I'm wondering in this one, if we looked at the values, at the point where at the end of the drought, whether or
mm.
not the data values are hovering around
Oh,
zero
I see.
and then went to one, or
Yeah, we
around one
can.
and then went to zero.
Ah, yeah, we can look into that.
We could, but it may be, we're not letting you complete your presentation, so maybe just go on and
Yeah, yeah, yeah. I think I understand what you mean. So the values of these cells at this point, right?
yeah.
Whether those are at this in this range, right?
It's more when you get further down, when you get to the end of all of the blanks.
Okay.
Okay,
So, so
the top of it's going from looking all white to things happening again.
so you can see my mouse moving, right?
Hmm.
Yes, yes,
So you mean these values
yeah,
right when the
yes,
drought ends, so
yes.
to speak?
The question is if you looked at the data lines just before that started up again and just after that started up again, is
Uh-huh.
it starting up again because
The
it's moved from around there to around
here.
there?
Oh, okay. Or here. Okay. Okay. Yeah.
Yeah,
Yeah. 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 Yeah.
yeah,
Um,
because the thing is, and this is more conceptual. We spent a lot of time
mhm,
figuring out why something happened when it happened.
mhm.
And I'd look at this, the question I'd have is, what happened to it was doing nothing for a long time, and then it started doing something again. What was the thing that made it move from doing kind of nothing to doing something again?
Uh,
Anyway,
okay. Yeah.
it's
Let
again.
me. Yeah. Yeah.
So the delta value actually for this one I think is 1. At least when I recreate it on my end, that's what I get. And uh, that is still, even when I run it numerically, I mean, with fraction precision, um, so infinite precision basically, it still does the same thing. So, um,
Right now, I wasn't suggesting that this was a sign of a bug. It was the thing that I was suggesting is the techniques that we were using to chase down the bug, maybe the same techniques that we could use to chase down an interesting, not bug effect, but actual effect.
yeah,
Yeah.
yeah, for sure.
Yeah. So these are very good observations. Yeah. Yeah. Thank you. So can we move on?
Yes.
Okay. So this is class 3, and this is class 4, similar jump, delta equal to 0.00453, here delta equal to 0.00454. So in this case, a different type of jump. I like to think of this as a frog.
Oh yeah.
Like a frog jumping. Anyway, yeah, so very interesting patterns.
What's
So
interesting
these are just
about the first one is really cool, just the way it is. And it's kind of some class 4 chaos, or yeah, on the border of chaos and order. You have some motifs repeated, and the second one, it looks like it does some stuff and then starts repeating.
yeah, that's true. That's true. Yeah, that's interesting. Yeah, that's a good observation. Yeah, it's qualitatively different.
Yeah.
Yeah.
And that's something that I see sometimes. That
Mm.
the stuff happens and then it gets into a rhythm.
Mhm.
That's those aren't too rare to just start finding
Mhm.
out in the wild.
Mhm.
That you don't have to engineer it to do that.
Yeah. Yeah, that's why this manipulate function is so powerful. I mean, users can just download the file and play with it and find all kinds of new phenomena which we have not yet observed. Yeah.
Yeah.
Okay.
It's fun to go exploring.
Yeah, yeah, exploration is fun. So section 2, intrinsic randomness generation and sensitivity to initial conditions. So basically here, okay, this will take a few seconds. Okay, there you go. So we use this
Triangular activation.
yeah, basically in reference 4, which is NKS book, Stevens NKS book, there are 4, let's see, page 150, right? Let's see. This was 160. This 150. Yeah, these 4 functions that he explores here. These are very, very instructive um, observations that Stephen makes here. And I use these 4 cases. Here in the case of continuous cellular automata, here is starting with one number in binary expansion. So and he looks at how these the iteration with of these 4 functions behave. So in our case, we use these activation functions. Let's see. And we start with either 1/2 or pi over 6. 1/2 has this simple digit expansion and or binary expansion, and pi over 6 has a complicated digit expansion. And so for example, here initial value is pi over 6. Initial value here is pi over 6 plus 10 raised to the power 20. So there's a difference here at the last digit here. This is how the continuous cellular automaton evolves in these two cases. And these are the differences, absolute values of the differences between these two. And here I plotted the average of these. For each row, took the average and plotted here as a function of the iteration. So after this many iterations, starting from here, so after about 200 iterations, it started showing these differences. Again, this is a manipulate function. Anyone can explore the different cases. And here are some results, some bitmaps of the results. Case A, as in Stephen's book, this function. Here, two things. The fact that these differences suddenly become non-zero after some point is sensitive dependence on initial conditions. The fact that, okay, there are these two parts for each case. On the left part, there's this, the initial condition is simple digit expansion, one half. And on the right side, it's complicated digit expansion, which is pi over 6. So the fact that we see this random looking behavior in both cases, especially here with the simple digit expansion case, means that we have intrinsic randomness generation involved here. Just like in Stephen's book here, in case A, there is, let's see, this is intrinsic randomness generation here in case A. I think he doesn't show this clearly here for each case. This for the differences, he only shows the case D, I think. No, here we difference. Oh, okay. Actually, he does for all four cases. Case A, there's this intrinsic randomness generation, just in the continuous cellular automaton case. Case B, we do have again sensitive dependence on initial conditions, and again intrinsic randomness generation. Case B also similar here in Stephen's book. In case C, let's see. Case C, it drops to 0 after some point. Here in the book, also it becomes 0. This is 0.00000. The significant digit goes to the right, so it approaches 0. In the case of case D, let's see.
There, the differences start pretty soon.
Yeah. Let's see. Let me see here. this is from my tech conference talk here. Yeah. In case D, we have a difference from what was observed in the case of this, starting from a single number. Okay. Yeah. In case D, when we start with the initial value 1/2, which is 0.10000 in the binary expansion, the result of applying this fourth function was like this. It dropped to 0 right away. Right? It became 0 after the very second step. But there was sensitivity
right,
to
because 1/2 goes
yeah
to 0 on that activation function. Looks like
yeah. So here the sensitivity to initial condition was there. When we change the initial condition slightly, it does the difference grows up. But in the case of the continuous cellular automata, uh, there is this intrinsic in this case, sorry, in the left case, the starting with 1/2. We have intrinsic randomness generation, whereas here the picture to compare with is this one. It goes to 0. It becomes empty. I mean 0, all the white cells. Okay, so that was the difference I observed here. Otherwise, the other results were similar. But in the case of continuous cellular automata, this is the difference I saw. Intrinsic randomness generation is still there. Okay. And are we going to be cut off, Dugan? It's 3 hours, I think.
no, there's no cutoff.
Okay. So in section 3, chaotic strings, as I was mentioning before, this is a special type of continuous cellular automaton. And let me show you the main function here. Okay, this is the chaotic string rule, cellular automaton rule for the chaotic string. So what's happening here is so T, there are these different functions defined here. T is this Chebyshev polynomial, second order Chebyshev polynomial. And T, this first argument 2 meaning Chebyshev polynomial second order, and T of 3 meanings third order. And this Q function I defined here, X is the main variable, and N and B are some parameters. So N is either 3 or 2. B is either 1 or 0. So when B is 0, this is the relevant part. So then it's just basically X. I use this finite accuracy for the computation. But basically, for B equal to 0, this Q function, Q of X, whatever the value of N is, either 3 or 2, Q of X becomes simply X for B equal to 0. For B equal to 1, this second term vanishes, so it simply becomes the Chebyshev polynomial of X. the corresponding order being this value of n, either 3 or 2. So that's those are the definitions for this cellular automaton evolution rule. So X, Y, Z are these three, again, we were talking about radius 1 neighborhood. So Y is the middle cell value, and X is the left, and the Z is the right cell values. So, so first, we have this T of Y, the Chebyshev polynomial of the central cell. And then we add to that this A is a parameter between 0 and 1. This parameter A, called coupling parameter, times the mean or the average of two things. The first thing is S is a parameter. Again, S is a parameter either, let's see, -1 or +1. S is either -1 or +1. And Q, as we defined earlier, Q of nxb. So X is this left cell value minus T and Y. So we know what that means. And the second term for taking the average is S times Q of nzb, the right one now, zb, minus T and Y again, this one. So this is the rule. So depending on the value of n, S, and B, these three parameters, we have 8 combinations. So those are called, they have these different names, 2A plus, 2A minus, and so on. Two of these are turn out to be equivalent. So effectively there are 6, but in principle there are 8 combinations here. So 8 so-called chaotic strings. So then, so from the perspective of continuous cellular automata, that's all we need to know at this point. There are 8 different continuous cellular automata with these different these rules. Okay, so we use 300 iterations, and for the delta, I called it, well, yeah, delta is 10 raised to the power minus 20, the small perturbation, and the logarithm I called epsilon. So 10 raised to the power minus 20 is the delta we use. Let's see. And we use either 1/2 or pi/6, these two initial values. The accuracy is 10 raised to the power 4 alpha. Okay. And this is the color code we use for the plot. Let's see. Yeah, let me make it smaller. Okay, minus this rainbow spectrum. This is -1, this is 0, this is +1. Everything in between has these rainbow colors. So this is the manipulate function, n equal to 2 or 3, b equal to check or uncheck. Check means 1, uncheck means 0. S is either 1 or -1. A is this continuous real parameter, and the initial value either 1/2 or pi/6. And so similar to before, except for the difference that there is this color code involved now, because these are real numbers. Oh, not, well, not just real numbers. These are between -1 and +1, real numbers between -1 and +1. So we have this color code. Earlier we had this gray code, 0 to 1 only. Okay, so this is for initial value pi/6, for example, and this is pi/6 plus 10 raised to the power minus 20. These are the absolute values of the differences between the two, and this is the average of the absolute values of the differences. And this is the example for 3A plus. So 3, n equal to 3, A meaning this B equal to 1, and plus meaning S equal to +1. Okay. And okay. And one other thing, um, um, according to Beck's um, theory, there are 26 special values of A, the A meaning this parameter. This, which I showed earlier. Yeah, in this rule, this parameter A, coupling parameter, there are 26 special values of this parameter A, and I used these 26 values of A, and these values have some uncertainty, and I used the value A minus the uncertainty and plus the uncertainty. So a little bit to the left and a little bit to the right. So for each case, for each value of A, I took these three values. So like this. So there are 78 cases to test how this behaves, how this type of calculation, what results we get for those 78 cases. So I did that. So here are the results. So these are bitmaps. Let me go to the actual outputs. So these are the actual outputs, yeah.
We zoom in on those differences.
Excuse me?
Let's zoom in on the green one.
Yeah, yeah. Let me make this a little larger.
Sure, yeah. There we go.
Yeah, maybe I can make it larger still. Okay.
Mm.
So this is the first of the 78 cases. Oh, actually, 200 would be optimal, I think. No, it's okay. 300. It'll make it bigger. But this is initial value equal to half and half plus delta, and this is initial value pi over 6 and pi over 6 plus delta. Okay, so these are the results. Okay, so from here, maybe we could use the earlier algorithm to take out these stripe patterns. So let's see, maybe let's see, maybe we can this. Yeah, maybe we can look at the bitmaps and then go to the other one to zoom in. So basically here we seem to have intrinsic randomness generation and sensitivity to initial conditions for many of these cases. Like, okay, there are 78 cases, so we'll go down the list here. 1, 2. Let's see. Okay.
Oh, you're paging down?
Yeah,
I see.
basically.
51
Yeah,
or something.
I thought it was not moving down, but actually it is.
Yeah, it's just
So
modulating.
yeah, after some point, yeah, we start observing some patterns here. Let's go to 53 here. let's see. 53. Um, 53. 56, 55, 53. Okay. So if we zoom in here, let's see. Let's zoom like this. We see some vertical patterns here.
Mm-hmm.
So I don't know if we can say this has intrinsic randomness generation involved. So I need to think about it some more, analyze it, maybe to see whether this is orderly or random. So this has some random features involved as well. But in all of these cases, we do have sensitivity to initial condition. So let's see. So 4, 75. Similar, I think, for 75 also. Um, 63, 75.
It's very interesting, the different shapes of the differences.
Yeah.
Like here, it's mostly the same except for these streaks down the center.
Yeah.
And for
So
others,
there's
it's
a
like
lot to, yeah.
for others, it's triangulars of different varying slopes.
Yeah, one person who came to my um, poster presentation, um, he or she mentioned that that the one in my hero picture of the on the poster,
Mm-hmm.
there's this parabola looking downward parabola looking shape, and that person said maybe this is this may be a hyperbola and it may have something to do with the Lorentz transformation formula. Uh, I don't know. And another person suggested the difference between the distance between this and this point where the difference starts appearing,
Mm-hmm.
that may have something to do with Lyapunov exponent. So those are great suggestions. I noted them down. I need to think some more about whether those are uh, relevant or
Yeah.
yeah. So anyway, uh, let's see. What was I going to say? Yeah. Here also a similar pattern here. So there's a lot more to explore, within these patterns, what these are telling us. Because the reason I'm focusing on these patterns is because um, um, as I said, in the Carl Detman's analysis of Christian Beck's this chaotic string theory, um, he points out. Let me show here. Um, Yeah, this is from my tech conference talk. So this is the quotation from Detman's uh, the abstract for his article. These results indicate that a theory of particle physics based on coupled map lattices must specify strong physical arguments for any choice of initial conditions and explain how stochastic quantization is obtained in the many stable parameter regions. So I need to dig more into his article. He has a different type of analysis, which is very interesting. I'm planning to uh, study in more detail. Um, but from this statement, I uh, I interpreted this um, um, uh, to mean let me see. Yeah. Uh, I think it boils down to these two questions. Uh, if chaotic noise is what is needed in order to simulate quantum noise, why do most of the physically relevant values of the coupling parameter correspond to stability rather than chaos? So I need to understand exactly what stability means in his approach. Um, um, and the second point is for making the correct physical predictions, why does it seem necessary to start with only certain special initial conditions? I think those are the two crucial questions. And of course, does this mean that the predictions are actually somehow already coded in the initial conditions themselves? Um, I don't think so, but I need to understand exactly what he means and um, make a
Yeah. So
um,
those
decision.
those functions that what were they called? Something Chebyshev.
Chebyshev, yeah.
Chebyshev. Yeah. And this author is using them to model some particle interactions.
Hmm. Yeah,
And he's wondering why something chaotic falls out of them.
yeah, yeah. Um, so I think um, I think that these two, I mean, whether it's sensitive to initial conditions, sensitively dependent on initial conditions, and whether there is intrinsic randomness generation. Those two are crucial, I think, to address Detman's questions, I think. Uh, the intrinsic randomness generation, I think, was misunderstood by many people. So that was my suspicion, whether that might be behind Detman's uh, question about whether um, the the parameter he says most of the relevant parameter many at least many of the parameters are in the stable region. So I need to understand what he means by stability. So I suspect that might have something to do with the intrinsic randomness generation. Um, uh, so I need to dig into it more. Uh, and regarding the his question about whether um, the initial conditions maybe some special initial condition may be necessary for obtaining the correct predictions. That might have something to do with the sensitive dependence on initial conditions. Um, so that's why that's the motivation for my explorations in this area. So that's why I'm plotting these to observe whether there is sensitivity to initial conditions, which seems to be true for all of these cases. But for as far as intrinsic randomness generation goes, that I need to study some more. Each of these cases, especially those cases where there seem to be these vertical patterns.
Mm-hmm.
So, okay. So that's so basically let's see. Yeah. So when exploring several continuous cellular automata, including chaotic strings, we have found both intrinsic randomness generation and sensitivity to initial conditions. But maybe not in all. Like in some of these cases, as I mentioned, I need to make sure that all of them involve intrinsic randomness generation. This should help to clarify Detman's questions regarding the foundation of chaotic string theory. So this is work in progress. So yeah, I would like to thank Dugan for all your help. And especially, as I mentioned before, this asymmetry thing on which we spent a lot of time today, which I think it deserves, a lot of time on this because, as I mentioned, our main results and the validity of our main results depend on that, numerical precision or accuracy, whether how reliable it is. Our results, the reliability of our results depends on those critical things which we spend quite a bit of time today. So I really thank Dugan and all of you who participated in today's discussions. I really appreciate it. So I'll review the video and do more study. So I really appreciate all of your participation. So I thank Xerxes for his support from the very beginning. He was the one who interviewed me the first time when I applied for the summer school, and I really appreciate his help and guidance throughout. And I really appreciate Stephen for kindly suggesting to me this project. And I really appreciate his deep understanding and foresight. So I think it's very important. This understanding this issue is very important for physics. So I think he's also I think interested. He wrote down the title of the book. I think he also plans to look into it. So I really appreciate Stephen's suggesting to me this project and for his guidance. And from the bottom of my heart, I thank Stephen and the entire Wolfram Summer School 2025 team for organizing the wonderful program, which has been very enjoyable and special to me. And I thank everyone involved. And for this talk, I really appreciate once again for all of you for coming and participating and And this helps me a lot to understand it better. As I said at the beginning, my goal was to share this update of my research with you, and your feedback means a lot to me. I'll look at the video and do some more exploration and investigation. And these are the references. It's in my computational essay. So thank you very much.
Thank you so much, Kiran.
Thanks, Kiran.
You're welcome.
Thank you.
You're welcome.
Thank you.